Okay, today we shall continue with the physical process models. In particular, we stopped on Monday on the chemical processes and the description of reaction kinetics. Again, you should consider this just a recall of things that you have already studied. So this shouldn't be nothing new to you from a theoretical point of view. What we are discussing here is how to convert our description of chemical processes into a kind of models that describes the reaction kinetics. You may anticipate that reaction kinetics are described or accounted for by the constant of reaction K. All the theoretical basis on which we build our models of chemical reactions, or in the context of physical processes, of chemical processes, is that of the law of mass action. You should have already heard about that. Schematically, we may say that we may describe a chemical reaction by saying that a certain quantity of chemical A is reacting with a certain quantity small b of a chemical quantity capital B for producing two products, capital C and capital D, in proportion small c and small d, lowercase c and lowercase d. How do we describe this process? We typically employ the law of mass actions, and we write that the variation in time of the concentration of one of the elements, let's say A, is, we may say these are the starting chemicals and these are the product chemicals. So the variation in times of the starting chemical A is equal by convention to minus a constant K that is called the constant of reaction or constant of chemical equilibrium times the concentration of A elevated to a power alpha times the concentration of B elevated to a power beta times the concentration of C elevated to a power gamma times the concentration D elevated to a power delta. This is called the law of mass action. In this definition, we may define N, alpha plus beta plus gamma plus delta, as the order of a reaction. So chemical reaction of the first order will have N equal to 1. To simplify or to exemplify, we may say that often chemical reaction depends on just one substance. Let's start by a chemical reaction that depends on just one substance. Then you convert this equation by saying that the variation in time of chemical C is equal minus K C elevated to a power N. And if N equal to 1, first order reaction, then we obtain this very well known differential equation, the C on the T is equal to minus K times C. And you know that the solution of this equation, the analytical solution, is a decreasing exponential. So C, the concentration, is equal to the initial concentration times the exponential that depends on the chemical reaction minus K multiplied by T. By convention, we know that these constants, the constant of reaction, strongly depends on temperature. And the dependence on temperature is accounted by a classical Arrhenius model. And the Arrhenius model is that the one that I've written down here. So the value of the chemical equilibrium constant at temperature T is equal to the value of the chemical equilibrium constant at temperature 20 Celsius degree times theta elevated to the difference time t minus 20. I assume that you already have known. This is the classical Arrhenius model that describe the dependence of reaction constants K on temperature. In particular, we may describe with this kind of models enzymatic reactions. What are enzymatic reactions? Are chemical reactions that depend on the presence of a substrate S and on the presence of an enzyme E. So that we may write that the substrate S plus the enzyme E is transformed into ES star, but is the activated complex S, so the substrate activated by the presence of enzyme E, and this transformation is described in the direction left to right by the K1 equilibrium constant. But simultaneously, we have a reverse reaction, so the activated complex deactivated, so that we have to describe it with a K2. So this is a two-way reaction, left to right and right to left. And then the third part of the reaction is the last chemical process in which the activated complex ES star is transformed into the product of the reaction plus a quantity of enzyme E0. The activated complex is unstable, meaning that ES star is in a steady state, or if you want, constant concentration, so that when a part of the substrate is activated by the enzyme, reversely, we have a deactivation process. Of course, the equilibrium of this process, these two chemical reactions, depends on the ratio between K1 and K2. The enzyme does not disappear during the reaction. Instead, we have an equation that makes that the totally of the enzyme E0 is equal to the employed part in the making activity complex plus the initial concentration E. This means that the enzyme during the chemical reaction, enzymatic chemical reaction, may be reused. Why are we interested in, or why we are introducing enzymatic chemical reaction? Because the enzymatic chemical reaction is a prototype of all the biochemical reaction. We know that most of the biochemical reactions are enzymatic reaction, meaning that depends on the presence of a substrate and are fostered by the presence of an enzyme E. How can we describe by employing the law of mass action? This reaction we convert immediately with descriptions by saying that the variation time of substrate S is equal to minus K1, so that is the process going from left to right. So the minus K1 times the concentration E times the concentration of the substrate S. I recall you that we are simply applying the law of mass action, nothing new. Plus the reverse action, K2, times the concentration of the activated enzyme ES star, of the activated complex, substrate ES star. Parallel, we may introduce a second differential equation describing the dynamic of the activated complex. So now we are describing the reaction that transforms the activated complex ES star. So we say that the variation time of ES star is equal to K1 times the concentration of E times the concentration of S, minus all the reactions that takes away ES star. So these are K2s, so the deactivation reaction of the activated complex ES star, that is K2, plus the transformation of the activated complex ES star into the product. So this is K3 times ES star. In order to complete this schema, we then introduce a third differential equation that describes the dynamics of the product of the reaction, so that we may write that the variation in time of a product is equal to K3 times the concentration of the activated complex ES star. We understand this is exactly 3 times application of the law of mass action to these 3 reactions. The reactions that are described by the constant K1, K2, and K3. So the reaction of activating and deactivating the complex, and the third reaction, that is reaction of transforming the activated complex into a product. So this is a very general model employed for describing enzymatic reactions. Because we are in steady state conditions, because this equation holds, we then say that the variation in time of the activated complex ES star is 0 in a steady state condition. This means that in equilibrium, and this is, I recall you, this is a dynamic equilibrium in which we have a continuous activation reaction, deactivation reaction, and transforming of the activated complex into the product plus initial concentration of the enzyme is 0. In a steady state condition, we say that, if you want, the constraints that describe the steady state conditions is that the variation in time of the activated enzyme ES star is equal to 0. So we will have always the same concentration of the activated complex ES star. I suppose that you have already seen this. In particular, we know, with some simple algebraic manipulation of these 3 differential equation plus the steady state conditions, we may write that the variation in time of a product P is equal to minus the variation in time of a substrate S, so is equal to the consumption of substrate X, and this may be typically written described by a Michaelis-Menten model, in which we have a mu max, so a parameter that we may call the maximum production or maximum production of the product P, and mu max depends on the temperature, times this quantity, that is an S concentration of the substrate divided by Ks plus the concentration of the substrate. This is the very prototypical model, but it is employed to describe the most numbers of chemical reactions, of enzymatic reactions, or biochemical reactions. In particular, we may notice that a production reaction, so a chemical reaction that transforms a substrate into some products of a reaction, but it is we are starting to introduce process of production. And I recall you that when we talk about production in this context, we are thinking to primary production or photosynthesis, or the transformation of chemical elements into primary production, that is algae or other elements, chemical machinery, that is biochemical machinery, that it is able to perform photosynthesis. In this case, we may see that if we study what happens when the substrate's concentration tends to infinity, so it grows indefinitely. We have a constant condition because the limit for s that tends to infinity of this quantity, s over ks plus s, it is exactly equal to 1. You may recall this is from the theory, mathematical theory of limits, but in order to calculate these limits, you simply make the derivative of the numerator divided by the derivative of the numerator, and the derivative is of the s variable. So that if we plot this function, we obtain a saturation curve like this one. Here we are plotting the velocity of reactions, v, as a function of the semi-saturation constant Ks. This is called the semi-saturation constant. Why this? Because when S is exactly equal to Ks, this quantity is 1/2. So when the concentration of a substrate is at Ks, we are at half of the maximum reaction speed. So if we plot the reaction speed as a function of Ks, we obtain these saturation curves. Well, these saturation curves, you may describe all the theory of enzymatic reactions. How do we do this? For example, let's consider the blue curve, the semi-saturation constant for the blue curve, that is Ks, is that value of the substrate concentration, so that you have half the speed of a maximum reaction. While the Ks grows, you end up with a saturation behavior, so that the speed of the concentration tends to the maximal concentration. By these plots, you may describe graphic all the behaviors in enzymatic reactions, all the different behaviors in enzymatic reaction. Yes, for example, with the blue curve, we have one possible shape of enzymatic reaction that is dependent when Ks is equal to Ks first, while the black curve is that obtained when Ks is exactly Ks with value. So let's start from the black curve. The black curve, when the constant concentration of the substrate is equal to Ks, so that the speed of reaction is 1/2 of the maximum value. If the concentration of the substrate increases, then the curve changes, so that, for example, when the concentration of substrates arrives to Ks first, the speed of reaction is exactly half of maximum speed. When I say that you can employ these plots to describe the effects of enzymes on chemical reaction, I mean that you can describe two categories of effects. The first one is induction plus increasing of the reaction speed, and the second one is inhibition. By induction, we mean the effect of increasing the number of enzyme, or the concentration of the enzyme, for example, by inducing of gene expressions of enzymes, or you may increase the enzyme's affinity to substrate. So in the first case, we simply increase the number of enzymes, and by doing this, what we do is we simply push this curve toward Vmax, toward maximum velocity of reaction, or we may increase the enzyme's affinity to the substrate. That means changing the chemical structure of the enzymes, so that the enzyme binds more easily to the substrate, so it is activated more easily. So you have another effect of increasing, inducing the speed of a chemical reaction. In the second case, you have a pushing of the curve toward the left, essentially meaning that the semi-saturation concentration is reached more quickly. Or you may consider the second category of effects, that is inhibition. Inhibition lowers the curve in the case of non-competitive inhibitions. So, for example, when you have covalent allosteric bonds, or you may have inhibition by the process of competitive inhibition. We may describe this by changing the form of the enzyme or the type of reaction. In particular, this is the classical lock and key description for enzymatic reaction. We may define the enzyme, we may describe the enzyme by this symbol, yellow one. We may describe the substrate by this symbol. So in this case, we have a perfect K and lock shaping so that the enzyme, the activated enzyme, has this form. A competitive inhibitor or competitive inhibition is obtained by introducing into a reaction a third chemical substance that has a compatible shape in terms of key, like the blue one, so that the blue one can easily lock or can easily combine to the enzyme, so that in this case you have the inhibitor that is lowering the number of available enzymes available to the process, to the chemical process. Otherwise, you may have a kind of uncompetitive inhibitor, like we may describe by introducing a fourth chemical element that somehow simulates the lock and key model, so that these uncompetitive inhibitors again reduces the number of available enzymes. The difference is that this chemical reaction is reversible, meaning that once the competitive inhibitor is combined with the enzyme, when you have a two-way reaction of linking and delinking, or coupling and decoupling of the competitive inhibitor to the enzyme, so that there is again a dynamical steady-state equilibrium, while in the case of uncompetitive inhibitors, this chemical bonding is not reversible, so that essentially what you obtain is a reduction of the available enzymes, but is a permanent reduction. There is a third number of inhibitions, a third type of inhibition, that is that of non-competitive inhibitors, that are chemical elements that link to enzyme in a very destructive way. So it's a way of disrupting the enzyme. If you want, sorry, this is a reversible chemical bonding. This is a semi-reversible, meaning that to reverse this chemical bonding requires some energy or some quite sophisticated chemical manipulation. On the contrary, the non-competitive inhibitor is a permanent disruption of the enzyme. Please note that all chemicals, all pharmaceuticals, medicines, work on this schema. So, for example, if you want to build medicines like paracetamols that lowers the temperature, the fever, you will introduce a competitive inhibitor like this one, but temporarily slows down the rate of reaction by making unavailable the enzymes. Other type of pharmaceuticals may be that of the uncompetitive inhibitor, so that you permanently block the enzymes from working so that the enzymes are then released through the excretion mechanism of the organism, so these are taken away from the body, or you may employ very disruptive mechanism like non-competitive inhibitors. This is typical what happens when you use how do you say, chemicals that are used, for example, for cancer controls, chemotherapics, like we call chemotherapics. Chemotherapics are therapics, chemicals that permanently destroys and takes away from the body the enzyme. Okay, why we are so interested in chemical enzymatic reaction? As I told you, because this is a very prototypical general way of modeling chemical processes in which there is a substrate involved. So the chemical reaction depends on the substrate, but there is also an enzyme involved, so a chemical object that speeds up or fosters the reaction. For example, when we want to model or introduce, or as we will see next week, a model for primary production, then we may employ this kind of models in which we think of the enzyme, like for example, as the production itself. Like for example, if we think that primary production consists of producing living organisms, like for example, algae, that are on their turn able to perform again primary production. So in this case, the algae itself behaves as an enzyme. So in this case, there is a kind of mixing of the role of the enzyme and of the products. The product itself acts as an enzyme, meaning that the more you have algae or primary productors into your system, the quicker will be the primary production process. You describe this kind of processes by employing Michaelis-Menten models. Okay, we will see how we may employ these Michaelis-Menten models for describing nutrient limitation of the primary production. We will see that next week when we describe the models for algal growth or chemical or primary production. Primary production in this context may be seen similar as algal growth, because algae growth or primary production. Okay, so let's now end this introduction on the chemical processes by describing how we may employ mass balance to model or to describe what happens into biogeochemical cycles. Biogeochemical cycles involve several different types of processes, like with assimilation or build-up of organic matter, excretion, changing of the speed of a reaction depending on temperature. So you may have several types of chemical reactions or chemical processes, or now we may call these physical-chemical processes that may be employed to describe the geochemical cycles. In order to explicitate what we are saying in quite vague or foggy terms, let me give you an example. As always, we start from an aquatic ecosystem. Let's, for example, things to a water body, dark blue. In a water body in which we have algae that are growing. You know that the water body interacts in one side from the sediment, so the water column interacts with the sediments, but the water column also interacts with the atmosphere. So this is a process of volatilization. This is a process of, if you want, atmospheric deposition. This is a process of resuspension, and this is a process of sedimentation. In particular, we may employ, as always, chemical balance, mass balance. So we start by writing that what it accumulates into the water column is equal to what goes in minus what goes out, plus minus what is transformed by chemical reaction. For example, let's focus on a biochemical model whose currency or state variable is nitrate and O3 minus. Then how we formalize mathematically this continuity equation. For example, we start by assuming that the variation in times of nitrate concentration, dN-NO3 dt. So this is the variation time of the concentration of nitrogen in the form of NO3 is equal to with discharge, so what comes in by the water discharge, times the concentration of nitrogen in the form of nitrate in the discharge water, in the incoming water, minus the concentration of out charge, so the quantity of water that is getting out from the system, times the rate of out charge, so the quantity of water that is getting out from the system, times the concentration of nitrogen in the form of NO3, minus, for example, a series of chemical processes. And we know that nitrate is typically taken away from water bodies by processes like denitrification. So this is the conversion of nitrogen in the form of nitrate into gaseous nitrogen, so NO3 and 2, this process is denitrification, plus the process that describes nitrification, so this is the chemical process that converts nitrate into nitrate, so K nitrification times concentration of nitrogen in the form of nitrate, minus what? A reaction process that we may call production. So a reaction process that depends on two constants, at equilibrium constant alpha times a speed of the reaction mu times the concentration of the algae itself. So here we are describing the nitrogen in phytoplankton. So these third terms describe the conversion of nitrogen in nitrate forms into phytoplankton. This process includes assimilation and build-up of biochemical matters or biochemical components. Okay. So you are starting to see how we may convert or how we may formalize our continuity equation that is obtained from the mass balance, that is simply a mathematical formulation of the principle of conservation of matter, into a process that includes transformation of nitrate, that is our currency or our state variable, into gaseous nitrogen and phytoplankton. This very general approach, mass balance approach, is the approach that we may employ to describe very complex processes, meaning that you can convert, for example, this is maybe a coastal zone, saltwater ecosystem in which you have microorganisms, crabs, these are echinoderms, crustaceans, fishes, and birds, and otters, for example, but in top top trophic levels mammals. You convert these kind of interactions by employing mass balance, so energy and mass conservation are the basic physical constraints in this case. You remember we have introduced physical constraints as constraints onto the differential equations that describe our process, so that we may, for each one of these elements, we may describe them as a box that is characterized by a biomass, so a quantity of organisms. This box grows as a consequence of a consumption process. So this is as a consequence of transfer of some matter from other boxes into the biomass box. Then this box decreases as a consequence of predation. So these are other elements in the trophic networks that take away biomass from the compartments and convert into their own biomass. Then you have catches and net migration or exports. So this is elements that are taken away from the systems, for example, fishery or migration, due to the fact that these organisms are motile, so they may decide or they may move to some other places. And so this rationale or this conceptualization of a model may be employed to describe very complex biochemical models up to describing networks, trophic networks, very complicated trophic networks like the one I am depicting here. We have already seen this trophic network. This is a model of Palude de la Rosa in the Laguna of Venice. So this is a mean annual model referred to year 2001. So these, the values, the figures that appears into the boxes, box and arrow models are referred to the year 2001 and are average that are calculated on an annual cycle, so that you can put figures as biomass in the box and figures as describing the importance of the magnitude of flows from one box to another. So in this case, for example, we may describe predation, that is the arrow that ends up here. The omnivorous species, they predate on carcinous are cancers. These are macrobenthic predators, other crustaceans forms. So omnivorous fish typically feed on carnivorous, mediobenthos, and also macrobenthos predators, but also they feed on macrobenthic suspended feeders, macrobenthic detritivorous, and lower levels, lower trophic level species, and so on. So this is a way to describe a mass balance by mass balance constraint, so by energy conservation constraint, a way of describing and conceptualizing an interaction models into quite complex model of trophic networks. Please note that this approach is the same, conceptually speaking, that you employ in a life cycle assessment evaluation. And for example, we build a life cycle assessment from cradle to grave, you may remember. So from the creation of an organism to its destruction, when you may describe all the flows and exchanges among the various elements appearing in the life cycle as a box and arrows schema describing interactions between the various elements. I recall you that the boxes are characterized by the biomass, including the box. So there is a figure that describe but refers to the magnitude or to the quantity of biomass referring to a specific type of organic biomass. And you have figures describing the flows that refers to the interactions between the various elements. Okay, now that we have introduced the basics conceptualization for the chemical, physical, and biochemical processes, we are ready to sophisticate our models by including some other processes that are of relevance in environmental systems. In particular, we shall describe now settling, resuspension, and other energetic factors like solar radiation, temperature, and photosynthesis. By introducing these models of these processes, we are ready to end up or to build a more consistent nitrogen biochemical cycle description. Let's start from settling and resuspension. In the aquatic environment, physical processes that determine the transport from the water column, for example, phytoplankton settling out from the euphotic zone, to the venting compartment and vice versa. The venting compartment generally is referred to as the sediment. And for example, nutrient resuspension is an example of a reverse process in which nutrients are moved from the benthic compartment or from the sediment toward the water column. In air, in this first case, we are talking about aquatic environment. On the contrary, in the air, we may find analogous processes, like, for example, atmospheric deposition, the typical process of settling, or the parallel process of settling, or we may include the processes like erosion due to the wind. Of course, we will not talk of these processes because we will lead us to very specific models. But the idea is that of giving you the tools, providing you or providing environmental engineers with the tools for understanding how these, for example, atmospheric deposition or erosion processes are modeled. Let's start by focusing on settling. The basic hypotheses on which the settling model we consider are founded are that of non-interacting particles, so we consider a dilute solution. So a water environment or a water column in which the concentration of settling or the concentration of elements that are settling is not too high, so a dilute solution, non-aggregated particles, so we shall consider the process of settling of single particles. Of course, this is not always true. Typically, you may recall that in wastewater treatment plants are processes like flocculation. So what are processes in which you shall describe the fact that some of these dilute or these dissolved particles may aggregate each other, building what we call flocculates. How do we describe a settling process? We start from a very general Newton law, in which we say that the mass times the acceleration of a particle is equal to the resulting of the forces applied to the particle. This is first Newton law, F equal m times A. Let's now describe the forces that are applied to a particle, suspended particle in a liquid or in a dissolved environment, we may identify three forces: a frictional force, a buoyancy force, and a gravitational force. The gravitational force is the force that is driving the particle from the upper part of the system down to the sediment. So this is due to the gravitational attractions of our planet. And the other two forces are reverse forces that describe the effect of friction and the effect of buoyancy. So the effect related to the fact that a particle in a liquid tends to float. How do we describe the forces? This is a very classical way. We may say that gravitational force is equal to the density of a particle times the volume times the gravitational acceleration g. The buoyancy forces is equal to the density of the flow of a fluid times the volume of a particle times again the gravitational force g. The frictional force, you may recall, is a force that depends from the square of the speed. So this force depends on the density of the fluid, on the drag coefficient CD, on the square of the speed of the settling speed of the particle divided by 2, and on the surface A opposed to the flow of a particle. A is a surface describing the area of a particle that is opposing, that is counteracting the attraction toward the bottom part of the sediment. In steady state, we may assume that the acceleration is 0, so constant speed of settling, so that putting all this together, we obtain the classical model describing the speed, the settling speed of a particle that is equal to 2 times the gravitational acceleration times the difference between the density of a particle, the density of a fluid, times the volume of a particle, divided by the drag coefficient, divided by the density of the fluid, divided by the surface opposed to the motion of the particle, and all this is squared. In the case of spherical particles, so there is a relationship between the volume and the area opposed to the motion, and you obtain a simplified version of this model in which the speed, the settling speed of a particle is equal to 4 times g times the difference in density of a particle minus the density of a fluid times a diameter referring to the size of a particle divided by the drag coefficient and the density of the fluid. This is the typical graphs that are employed by engineers when they are describing condition of flows. This plot describes the relationship between the drag coefficient CD and the Reynolds numbers. The Reynolds numbers may be expressed as a function of the, if you want, the diameter of a particle, the density of a fluid, and the settling speed or the speed of a particle itself divided by the, this is not the density, but it is instead what is this other quantity? The mu is not the density. I don't recall the word now, but it will come to my mind soon. Anyhow, we see that depending on the different shapes of a particle, spheric particle or cylindric particles, and depending on the condition of the flows, so a condition of the flows are described by the Reynolds numbers, the drag coefficients are described by this kind of curves. In laminar flow conditions, you have a low value of Reynolds number. Yes, mu is the viscosity. Sorry, I forget the word. For low values of Reynolds number, you are in condition of laminar flows. For higher value of Reynolds numbers, you are in conditions of turbulent flows. In this case, we have Stokes law, but it is applicable for laminar flows conditions. So low value of Reynolds numbers and spheric particles. In this case, we have a simple relationship between the Reynolds number and the drag coefficient. The drag coefficient is 24 divided by the Reynolds number. If you put this together with the relationship we have obtained from the first law of Newton, we obtain an explicit description of the settling speed of a particle. That is what we call the Stokes law. So the settling speed of a particle is equal to the gravitational force divided 18 times the viscosity of a fluid times the difference between the density of a particle and the density of a fluid times the square of the diameter of a particle. For other shapes, what is typical of, for example, other forms of algae, phytoplankton, we may find an equivalent radius or a correction factor in order to modify the Stokes law. For other conditions, like that of turbulent flows, in which we have high value of Reynolds numbers, and for cylindric particles, we may assume a drag coefficient of 1. So you see we are in this area. A drag coefficient of 1, in this case, the speed of a particle is more or less approximately equal to this quantity. Please note that all these descriptions are obtained from the first law of Newton applied to a single particle suspended in a fluid. I recall you that the assumption is that of diluted fluid and non-aggregating, non-interacting particles. In this case, we have the Stokes law of the laws for turbulent conditions flows. This is an explicit physical model derived by physics that allows us to obtain the speeds of a particle. In general, we may obtain some more sophisticated description, which may be called an empirical or a simple empirical description, in which we have no constant. And how do we, the modelers, the environmental modelers, describe this kind of processes? Of course, we describe it by a first order kinetic. We like to simplify our life. How we may do that? We may simply write that the variation time of the mass of the suspended particles in the water column is equal to minus a rate of removal by settling S times the concentration of the quantity of the suspended material. So we write a first order kinetic, which by constant S, or the rate of removal by setting, is made equal, of course, to the speed, the setting speed of a particle, as we have calculated, or we may measure, divided by the depth of the mean depth of the system. By this kind of description, we may derive that the rate of removal by settling is equal to the differences in densities of particles and of water divided by viscosity of the water. So we have obtained a model that describes the rate of removal by settling by simply a dependence on the difference of the density of the particle and of the densities of water divided by the viscosity of water. So here we have characteristic of water, the viscosity, characteristic of water, the density, and characteristics of the particle that is settling, so the density of particle. What is the density of particle? Of course, a particle may be seen as made up of aggregated smaller subparticles. So the density of particle is a description of the level of aggregation of this particle. We have two experimental plots, two experimental descriptions of this quantity. You may recall when we have looked at the characteristics of the most common solvent on the earth, that is water. We found some curve describing the changing of this characteristic with temperature. In particular, we have seen that for density of the particle, we have a shape like this one. I recall you that the maximum of the density value is at 4 Celsius degree. So here we have more or less the maximum. And then you have a decreasing shape, a decreasing form with increasing temperature. So with increasing temperature, the viscosity, sorry, the density of the water, of course, is decreasing. As well, you may have the same description if you focus on the characteristic viscosity. The viscosity of a particle decreases as well, increasing with temperature. So with an increase in temperature, you have a decrease in density and a decrease in viscosity as well. So that from this submodel, you may obtain a dependence of the sedimentation rate or rate of removal by setting S, but we have been able to express it as dependence from the density of particles and the viscosity of the particles. Then, depending on the density of particles and on the temperature, you have different settling, different sedimentation rates, and the different sedimentation rates are described by these curves in terms of dependence of the sedimentation rate on the temperature. What we may deduce quickly by this kind of graphs, we deduce that for all density of the particles, when the temperature increases, the sedimentation rate increases as well. So, if I ask you, what do you expect will happen to the settling rate or the sedimentation rate or the speed of transfer from the water column to a sediment of a particle as a dependence of the temperature, you shall answer that as temperature increases, the sedimentation rate or the speed of transfer of particles from the water column to the sediment increases as well. Okay? So this is more or less what we may employ for describing or for building a settling model or a process of sedimentation or a process of transfer of biomass or masses from the water column to the bottom sediment. Now let's try to build a model that describes the reverse process of settling. As I told you, the two processes that describe interaction between the water column and the sediment are settling and resuspension. We have just introduced a model that describes settling. Now let's give a look to a model that we may employ to describe resuspension. What are the factors playing a role in a resuspension process? What is resuspension? Resuspension is the movement of substance from the sediment onto a water column. We may, for example, describe our water ecosystem. We have a distance from, let's say, an arbitrary original point, and we have a depth of the water system that is described by this capital H, and you may have waves on the surface of water. Why do we introduce or we want to describe waves? Because, as we will see, are waves that generates the process of the suspension. Waves may be described by the speed v of the moving wave, by the hs of the wave itself, and by the period t equal to length of the wave divided by the speed. So this is the period, time from what one maximum value of the wave to the other two subsequent one. L is the wavelength, H is the period, or if you want, the frequency. Another important aspect that is related to the transfer of wind energy U to the water system is the fetch. The fetch is a length that refers to the surface length of the water system that is exposed to wind. So the bigger the fetch, the larger will be the quantity of energy transferred by wind to the water. We may represent these effects by drawing the surface of the water as a wavy surface, so we may have an increase in wave height and a decrease, or an increase also in a wave period as a function of the fetch or the distance. And as a consequence of the generation of waves, we have that the energy in water, depending on depth of the water, is transformed into gyres that we may represent in this way. So, to a water that is moving on the surface as a consequence of the wind blowing on the surface, you have a generation of a loop in the bottom part of the water. So due to the viscosity of the water, we have a generation of this kind of loops that propagate, due to the viscosity of water again, into smaller and smaller loops. When these water movements that are described here or depicted by these loops reach the bottom of a water body, you know that this movement of water, in particular in this part, very close to the bottom, are horizontal movement of the water. This horizontal movement of the water generate a stress that is maybe called the shear stress, and we may indicate tau. With tau, a stress is a force. Of course, an horizontal movement of the water generates a vertical shear stress, vertical toward the top. So the wind is flowing, the wind is blowing, the blow of the wind happens along a length that we may indicate with fetch. The bigger the fetch, the higher the waves generated, and the lower the period. So we have lower period waves with higher height. This generates loops, water loops, that are propagated from the surface of the water body down to the bottom part of the water body. When the depth of the water body decreases, this means that when we are reaching toward the shallower part of the water body, then this water movement generate a shear stress tau on the sediment that may be seen as a vertical force that is moving sediment toward the upper part. Then we have to introduce another characteristic, that is describing the characteristics of the sediment, and we may call it critical shear stress tau c, that depends on the sediment, grain size, on the sediment grain size distribution, or on the sediment consolidation, or if you want, on the water content of the sediment. So now that we have all the elements, the shear stress generated by winds that generate itself, these loops, generates a force, and you have a reverse force that we may call the critical shear stress, but is a vertical downward force that keeps the sediments from being suspended. We are ready to introduce a model, or to build up a model for describing this process. And this model may be written or conceptualized in this way. Let's say epsilon is the quantity of a suspended material from the sediment. We may say that the quantity of the suspended material is 0 if the shear stress generated by waves is smaller than the critical shear stress. Instead, by some empirical observation, we may build a model that describes the quantity of resuspended materials when the shear stress is larger of the critical shear stress. And in this case, we may write that the resuspended material is equal to a quantity coefficient, let's say alpha divided tau Td, times the difference between the critical shear stress and the shear stress elevated to a cube. This is a typical cubic dependence of the frictional process. This is a frictional process. You may remember that frictional processes depend on the square of the velocity, the square of the speed, and from your physics classes, you may recall that the force generated by this movement, by this frictional movement, is proportional to the cube of the force exerted. So we have a resulting of the upgoing force. I recall you that this is the modulus of a shear stress that is bigger than the modulus of a critical shear stress, so that this quantity is positive, so that your cube of a positive quantity is positive. So we have a positive, this means going to up force that is moving material. By experimental observation, alpha is often found equal to 0.008, and tau d, that is expressed in it is a force, because we are normalizing this force, but it is comparable to this quantity, that is undimensional quantities, r-dimensional quantities. So this quantity, we have a force divided by a force multiplied by an dimensional quantity. This is an dimensional quantity describing the quantity of resuspended material. And we know that for shallow water system, so for water systems that are not too deep, we may find a dependence of the shear stress on the speed of the water speed at 15 centimeters from the bottom. So we have, for shallow water bodies, an explicit mathematical model that links the shear stress tau to the square of the water speed at 15 centimeters from the bottom. Why 15 centimeters from the bottom? Because you know from your flow classes, but if you describe a flow in a tube, the speed flow of the walls of the tube are 0. So by convention, we assume that in order to calculate our suspension model, we will evaluate the speed of the water at 15 centimeters from the bottom. And then we have another submodel that for shallow water system describes the dependency of the speed of the water U from the depth of the water system H and from the period of the waves and from the wavelength L. Please note that this dependence with description links the speed at 15 centimeters from the bottom to the H of the wave, Hs, to the period of the wave, tau s, to the depth of the water system, H, and to the length or the reverse of this is 1 over the times of the wave. Please note that this model simulates the effect of wind, but not the effect of currents. So by employing this kind of models, we are just transferring the effects of winds as generating waves and generating movements as producing a shear stress that is responsible of suspending materials from the bottom. This is the most general model you may find to describe the suspension in water bodies. You see there are a lot of assumptions. In particular, the key assumption you should recall is that the speed of the water is that of 15 centimeters from the bottom. You may, for example, estimate the suspension by this model by measuring the speed of the water at 15 centimeters from the bottom. Okay, this is a practical way of estimating the suspension by a model. There are other relationships that are obtained by experimental observation. For example, here we have a relationship that is linking the mean velocity at 15 centimeters above the bottom with the size diameter of the particles. So this is a way for estimating tau critical or the effect of tau critical. So we are describing here the effect of tau critical as a consequence of the movement of the water, of the sediments of 15 centimeters above the bottom. So here the sediments are moving with the water at 15 centimeters above the bottom as a consequence of the waves. And depending on the size, diameters of the particle, grain size, and depending on the consolidation degree of the sediment, we obtain 3 different movements for the particles on the water bottom. And these movements are erosions, that means movement of resuspended particles from the bottom side, and you will have erosions when the size diameter of particle is in this area. For example, you may fix, let's see if I can confuse you more the idea by making some annotation. You may fix the size diameter of a particle let's say it is something less than 10, then depending on the degree of consolidation of particle, that may be 90, 80, 70, 60, 50, these are densities of a particle. So depending on the water content of the sediment, degree of consolidation of a particle, then you may obtain different movement transportation that are one erosion, but is horizontal movement, deposition, that is settling, or transportation, that is simple movement on the bottom of the particles. You see, by this graph we obtain a relationship between the characteristics of the sediment in terms of size, diameter, and consolidation degrees, and the speed of the sediments at 15 centimeters above the bottom. Of course, the speed of the sediments has, as a consequence, different movement types, that means one, erosion, taking away the sediment from the bottom, transportation, that is moving the sediments on the bottom, and deposition, that is transfer of the sediments from the water column onto the sediments area. Okay? This ends up our description of the physical processes settling. So up to now we have described settling and the suspension. Now we shall finish the lecture of today by introducing models for describing other physical processes like energetic factors. Let's see, what time is it? 10:51. Give me 10 more minutes or 5 more minutes when we will finish. Let me introduce our energetic factors. In particular, let us introduce models describing the effect of solar radiation. We have said that solar radiation is the main energy source for our ecosystems. In particular, this is relevant in order to describe a relevant process that we have identified as primary production. And we have seen that the solar radiation is the main forcing function for many ecological processes like photosynthesis, photolysis, meteo, evapotranspiration, and so on. How do we measure the effect of solar radiation? Trivially, we know from Planck radiation, from the Planck relationship, that the energy associated with radiation is equal to the constant of Planck 8 times the radiation frequency nu, or we may rewrite it as 8 times the speed of light c divided by the wavelength c, the wavelength lambda. We have already said that Earth's surface lowers the quality energy in the sense that photons are absorbed in the visible or ultraviolet spectra and retransmitted in the infrared as thermal radiation. How can we describe this process? We start, first of all, making an energy balance. We have already seen this energy balance. These plots describe the fate of solar radiation as described by the solar constant. So we have seen that this energy transfer from the sun is in balance on the surface of the planet, meaning that taking away the reflected part, reflected by dust, gas, clouds, and albedos, then there is a part that is absorbed in the atmosphere, and all the rest, it is absorbed by the Earth directly and indirectly, generating tides and current. The point is that all this energy balance is in equilibrium. So that if you make 65% what is emitted by the atmosphere into the troposphere plus the 35% that is immediately reflected, then you have 100% of this energy. So the solar constant 1360 watts per square meter. We have different types of transformations. In particular, 9% of the band of the solar radiation is ultraviolet radiation. So very small part, 9%, less than 10% is ultraviolet. And this ultraviolet may be subdivided in terms of wavelength, less than 0.12 micrometers and in the range 0.34 micrometers to 0.40 micrometers. Of these, we may describe all the different phases. For example, 4% of this radiation is absorbed and reflected in the stratosphere, while of 41% of this band is visible. And the visible is it reaches the Earth and is reflected after being used or transformed by degradations in ecosystem. Please note that half of a percent of a band of the solar radiation is 50% infrared, so thermal radiation, and this is absorbed and reflected from CO2 and various other gases in the atmosphere. How do we describe in our models the energy transfers? We employ generally these units. The classical one is the units of the solar constant, watt per square meter, or the British thermal units, or the Langleys or kilocalories, or small calories per square meter per seconds, or megajoule per square meters per day, or finally Einstein's per square meter per seconds. Einstein's are moles of photons per square meter per second. So you may employ all these units or these currencies. Typically, the conversion factor between the general currency, watts, BTU, Langley, calories, and megajoules are this one. While for the Einstein, we do not have a conversion factors because, of course, the Einstein being just a quantity of photons without an indication of the type of photons, and you know that photons are characterized by the wavelength. The Einstein is interesting because the Einstein counts the photons in terms of moles, density of moles per unit surface, unit time. Cannot be converted in above units, but it is used in photosynthetic active radiation because we may say that 9 moles of photons, so 9 Einsteins of photons in the visible rate are necessary to fix 1 mole of oxygen. We, a stoichiometric calculation that allows us to calculate a conversion factor in the process or fixations of photons or utilization of photons to fix chemical elements in order to produce oxygen. So this is a very useful way of measuring the process of photosynthesis. Then, I think we stop here now, and we will start back next week by describing the models that we may employ to describe the effect of solar radiation on the surface of the sun. And we will see that the effect of solar radiation depends on the photoperiod, so which day of the year and which part of the year we are looking for, and the yearly angle, by the yearly angle and the solar declination. We'll see in details with models next week. We stop here. I know I've been a little bit long today, but it was necessary. If you have any question, I stay 5 minutes more in the class. Otherwise, we shall meet next Thursday.